200 feet beneath the Hudson River, inside concrete walls, poured during the Taft administration, a slow-motion disaster has been spreading since 2012. Saltwater. Trapped inside the bench walls of America's most critical rail tunnel. Slowly, quietly, eating away at the steel that holds everything together. And the project meant to replace this aging structure. A mega project, with a total price tag now climbing toward $50 billion, depends on the old tunnel surviving long enough to finish the new one. For nearly 8 years, the engineering reports describing this deterioration sat in technical archives accessible to anyone who knew where to look, but rarely making it into the public conversation. Now, with construction finally underway on the new tunnel, the math behind that race is starting to look terrifying. When the North River tunnels first opened, the Wright brothers had only been flying for 7 years. The year was 1910. Henry Ford had just released the Model T. Steel-frame skyscrapers were still considered experimental, and 2 cast-iron tubes, each barely wide enough for a single train, had been drilled through silt and rock beneath one of the busiest rivers on the planet. They were called the engineering marvel of their generation. And for over 100 years, they performed. Every single weekday, more than 450 trains passed through them, carrying around 200,000 passengers between New Jersey and Manhattan. That's roughly the population of Salt Lake City, moving through a 1910 tunnel every business day. By the early 2000s, engineering surveys were already flagging concerns. Concrete was aging, joints were stressed. The constant rhythm of trains was taking a measurable toll. But these issues, while serious, were considered manageable. Then came the night that changed the calculation entirely. On October 29, 2012, the storm everyone had warned about for decades finally arrived. Hurricane Sandy didn't just hit the East Coast, it rewrote it. The Hudson River surged, storm walls were overrun, and within hours, both North River tunnels were submerged in saltwater. Engineers later estimated that approximately 13 million gallons of seawater poured into each tube. The water didn't just flood the tracks, it filled the bench walls, the concrete structures running along both sides of the tunnel that house electrical cables, signal systems, and ventilation lines. And here's the part that didn't make headlines. When that water eventually receded, it didn't simply drain away. Saltwater leaves something behind. Chlorides, microscopic ions that don't evaporate. They settle into the porous structure of concrete. They migrate, and they begin a chemical process that older tunnel designs were never built to resist. Within months, engineers were already documenting accelerated corrosion. The kind of corrosion that doesn't show on the surface for years. The kind that can hollow out a structural support from the inside, while the outside still looks fine. The clock that had been ticking on this tunnel for 100 years suddenly started moving a lot faster. Saltwater doesn't just sit on a surface. To understand what's actually happening inside these tunnels right now, you have to understand a process called chloride-induced corrosion. Concrete, on its own, actually protects steel. The high alkaline environment forms a passive layer around rebar, a microscopic chemical shield that keeps oxygen and moisture away from the metal. But chlorides break that shield. Once chloride concentration reaches a critical threshold inside the concrete, the protective layer dissolves. Oxygen and water reach the steel. Rust forms. And here's where physics gets brutal. When steel rusts, it expands, sometimes by as much as 6 times its original volume. That expansion pushes outward from inside the concrete, creating internal pressure the structure was never designed to handle. Cracks form, concrete spalls, meaning chunks break off. Water gets in deeper. The cycle accelerates. In structural engineering, this is sometimes called concrete cancer, and the damage progresses slowly, almost invisibly, until suddenly it doesn't. Engineers tracking the North River tunnels have been measuring chloride levels in the bench walls for over a decade. The readings have not been reassuring. Some sections show contamination well above the threshold where corrosion typically begins. Other sections show visible deterioration. Concrete is crumbling. Bench walls are losing structural integrity. The very surfaces that house the tunnel's nervous system, its power and signal cables, are degrading faster than anyone originally projected. Between 2014 and 2022, a series of engineering assessments quietly piled up in the offices of Amtrak and the Port Authority. They weren't secret. They simply weren't loud. These technical reports laid out in dense engineering language what was actually happening inside the bench walls. Chloride penetration, rebar corrosion, reduced load-bearing capacity, estimated remaining service life dropping with each new round of inspections. Some of the more sobering documents suggested that without major intervention, sections of the tunnel could face mandatory closure by the early 2030s. That wasn't a worst-case scenario buried in an appendix. It was the working assumption guiding the entire rehabilitation strategy. The reports were technically public, but they didn't generate cable news segments. They didn't trend on social media. They lived inside technical PDFs that almost no one outside the rail and infrastructure community ever read. And for nearly 8 years, the urgency described inside those documents was wildly out of step with the urgency outside them. Most commuters had no idea their daily ride was happening inside a structure on a tightening clock. The plan to fix this is staggering in scope. 2 new tunnels beneath the Hudson, completely new tubes with modern design, modern materials, and modern safety systems. Then, full rehabilitation of the original 1910 tunnels once the new ones are open and traffic can be diverted. New bridges, new track, new stations. Across the entire Gateway program, cost estimates have grown dramatically over the past decade. Early projections in the 2010s landed near $16 billion for the tunnel portion alone. As designs matured, inflation hit, and the full scope of rehabilitation became clearer. That number kept climbing. The full program, tunnels, bridges, supporting infrastructure, is now widely estimated at $40 billion and rising, with some long-range projections approaching $50 billion when contingency financing and regional connections are included. To put that in perspective, that's more than the entire annual federal highway budget. It's larger than the GDP of most countries on the planet. And every single dollar of it is being spent toward a single objective: keep 2 of the most economically important tunnels in the United States from failing before their replacement is ready. Here's where the math gets uncomfortable. Construction on the new Hudson Tunnel began in earnest in 2023. The current target completion window stretches into the early 2030s. The rehabilitation of the existing tunnels can only begin after the new tunnels are fully operational, because closing one of the existing tubes for major repair work would slash capacity on the Northeast Corridor in half. So the schedule is dependent on a chain of completions, each one tied to the next. New tunnel finishes. Old tunnel goes offline. Old tunnel gets rehabilitated. New tunnel takes the load. That sequence assumes the existing tunnels hold up. The engineering data suggests they probably will. The engineering data also suggests there is no comfortable margin. A single major incident in one of the old tubes, serious fire, a structural failure, a power system collapse triggered by corroded cabling could force an emergency closure years before the new tunnel is ready. And that scenario is not a fringe possibility. It's a known risk that planners openly factor into their timelines. The replacement isn't being built to a finish line. It's being built against a deadline no one can see clearly. Imagine a Tuesday morning when one of the two tubes finally has to close. Capacity through the Hudson River corridor would drop from roughly 24 trains per hour in each direction to around 6. Amtrak service between Boston and Washington, the busiest passenger rail corridor in North America, would be paralyzed. NJ Transit would lose the ability to move tens of thousands of commuters into Manhattan during peak hours. Roads would not absorb the overflow because they're already at capacity. The Lincoln and Holland tunnels for vehicles cannot expand on demand. The path system, also undersized for that kind of volume, would be flooded. Economists have estimated that an extended closure of one tube could cost the regional economy on the order of $100 million per day in lost productivity, delayed shipments, missed work, and broken supply chains. Stretch that across weeks or months, and you're looking at one of the most disruptive infrastructure failures in modern American history. That's the scenario sitting underneath all the headlines about budgets and groundbreaking ceremonies. The race isn't really about building a tunnel. It's about beating a deadline that nobody can predict with certainty. Construction crews are now drilling on both sides of the river. Tunnel boring machines are being assembled. Concrete is being poured into shafts that will eventually connect under the Hudson. Federal funding has been committed at a scale that didn't exist for most of the past decade. And inside the old tunnels, monitoring sensors track every inch of bench wall, every chloride reading, every micro crack. Whether the new tunnels arrive in time depends on factors no one fully controls. Construction risk, material costs, the sheer chemistry of concrete that's been absorbing salt water for 13 years and counting. What started as an engineering problem in 1910 has become one of the largest construction races on the planet. And the answer to whether $50 billion will be enough or arrive in time won't be clear until the first new train rolls through sometime in the next decade. Until then, every weekday morning, 200,000 people will keep boarding trains that pass through walls, slowly turning into something their original engineers never planned for. If you want to follow more mega projects exactly like this, the high-stakes engineering races most people never hear about until they either finish or fail, subscribe and stick around for the next one.